We will now discuss integer programming, wherein the major strategy or technique is branch and bound method. So what is integer programming? Integer programming differs from linear programming in that they require some or all decision variable values to be integers or whole numbers. It can take the form of any of the following. First is pure integer or all integer models that require all variables to be integers, no exceptions. Another is mixed integer or MILP, mixed integer linear programming models that require some variables to be integer but allow the remaining variables to be continuous or non-integer. Or when we say continuous, those with decimal positions or in fraction form. And the third form is your 0-1 integer models that require all variables to assume a value of either 0 or 1. This one is applicable for situations wherein there are two possible decisions only. It's either a yes or a no, or a male or a female, or a Coke or a Pepsi, or whatever situation, so long as the decisions would be limited to just two. Now, what are some of the possible solution approaches to integer programming models? You have linear programming with rounding off. You also have complete enumeration. The third is the cutting plane technique. And the fourth is partial enumeration via branch and bound. Let me discuss each one at a time. I'll begin with linear programming with rounding off. Based on how it is described or written, it is simply proceeding with your usual linear programming technique, and then if the solution you got has decimal positions, then you just round off. Rounding off linear programming solutions to linear models with integer restrictions is the most common or practical approach, because as I've said, all you have to do is to round off your solutions if they are continuous in form. However, this approach has two pitfalls. First, the rounded solution can be far from optimal. Second, it may be impossible or at least extremely difficult to round off the variables and still satisfy all the constraints. Let me explain. Let's say in your mathematical model, one of the constraints is that x sub 1 should be less than 10. Okay. If, based on your company's practice, you have the practice of rounding up your values, okay, meaning no matter how small or how large the decimal position is, you're simply going to round it up. So, when you did a mathematical modeling and you computed the solution for x sub 1 is equal to 9.8, okay, which is less than 10 based on the constraint that we discussed earlier. But since your company's practice is that no matter what the decimal position is, you would simply round it up, then you are going to use x sub 1 equal to 10, which negates the constraint whereby x sub 1 should be less than 10. That's why in the second bullet, it says there it may be impossible or at least extremely difficult to round off the variables and still satisfy all the constraints. For the previous bullet, the rounded solution can be far from optimal. Okay? There are other companies wherein the rounding off practice is that no matter what the decimal position is, simply remove the decimal position. Meaning you don't anymore round up or round down. Okay? You just accept the integer portion of the solution. So let's say in your mathematical model, your objective function equation is to maximize profit, and then the equation includes 3,000 pesos for every x sub 1 that you produce. And then when you did your solution methodology, you found the x sub 1 value to be equal to 50.8, which is very close already to 51. But since your company's practice is to disregard the decimal position, then you're just going to assume x sub 1 to be equal to 50. 50 multiplied by 3,000 is much lower than 50.8 multiplied by 3,000. That is the meaning of the first bullet there. The rounded solution can be far from optimal. But if you are aware of these pitfalls and you can remedy the pitfalls, then rounding off linear programming solutions to linear models with integer restrictions is the most common or practical approach. It's the easiest way in coming up with an integer solution. Another solution approach is complete enumeration. Complete enumeration involves the evaluation of all possible combinations of decision variable values. Take, for example, a luggage with a rotary lock, or any rotary lock like the one used in bicycles. Let's say you locked your luggage and kept it for a relatively long time. And when you again had to use your luggage, you cannot anymore remember the lock combination. What do you usually do if that is the case, other than destroying your luggage? For most, they would try to determine the combination of the luggage, beginning with 000, 001, 002, 003 until the lock clicks open. That is what is meant by complete enumeration. You have to test for each and every possible value that a variable can assume, as well as to test for each and every possible combination of values that all variables involved can assume. So this one is better than linear programming with rounding off in terms of accuracy, because if you would be able to send or to test rather all of the possible values of each variable as well as the combination of all values of all variables involved, then you are bound to get the best solution. It's just that doing so is going to be quite tedious. So this approach will provide an optimal solution, but it is a viable approach only for relatively small problems, like if you only have 3 variables and each variable can assume values from 0 to 9. Because what if you are involved with a scenario wherein each variable can assume values from 0 to 99 and you have 10 variables? Then the process of complete enumeration would be very tedious. Okay. Still, in terms of accuracy, this is better than linear programming with rounding off, because if you would be able to complete this process, then you are bound to get the best solution. The third solution approach to integer programming is cutting plane technique. The basic idea of the cutting plane technique was to ignore the integer restrictions initially and then solve the model as if you are solving a regular linear programming problem. Non-integer optimal solutions were then cut off by adding an additional constraint to the model that would exclude the non-integer point but would not exclude any integer points. How is this applied? If you would recall this graph, the one we used in the solution for the first example using the graphical solution method in linear programming, our optimal solution was found at point C. It's just that if you would recall, at point C, the value of x sub 2 is 42.5, which is not an integer solution considering that it has a decimal position. So what does the cutting plane technique suggest? It suggests that if you have a solution that contains a non-integer value, then you simply introduce new constraint equations represented by new lines that would eliminate the solution that gave us the non-integer value. And you continue introducing new constraints represented by new lines until you end up with an optimal solution wherein all the values of the variables are integers. As to how you're going to come up with new equations or new constraints represented by new lines, then that is subject to trial and error, which is something that I am not suggesting. It's just that this is one of the techniques discussed in other books that I'm also discussing it here. But again, it's not one of the best techniques in terms of integer programming. So among the three that we have discussed so far, in terms of accuracy, the best is complete enumeration, but the most practical is your linear programming with rounding off. Now, since the best in terms of accuracy is in terms of your complete enumeration, it's just that it's going to be very tedious if the number of variables involved is quite numerous, as well as the number of values that each variable can assume is also quite numerous. Then we have a fourth approach in solving integer programming models, and that is partial enumeration via branch and bound. As it suggests, you don't have to complete the entire enumeration process, meaning you don't have to test for each and every possible solution or combination of values. You just have to concentrate on those combinations that are deemed they are still worth pursuing, and you separate those that you think are not worth pursuing. Okay? For example, in the luggage scenario, if that is your luggage, then you may want to test first combinations of values that are familiar to you, like your birthday or specific combination of values that are memorable to you. You don't have to begin with 0, 0, 0. Okay, that's why in that particular instance, 0, 0, 0 might be something that you don't want to pursue anymore. Okay, but you only pursue those combinations that you think might be the correct combinations based on your knowledge of specific values that are memorable to you. That is what is meant by partial enumeration. In effect, you would have two buckets. One is considered promising, the other is considered as not promising, and you concentrate only or focus only on the promising combinations, which would reduce the tediousness of complete enumeration. And partial enumeration is done using the branch and bound method. Partial enumeration determines the optimal solution by examining only a portion of all possible combinations of integer values. The procedure basically divides the set of all solutions into subclasses. So, what is branch and bound? Branch and bound procedures partition the set of all solutions into smaller subsets and then search among promising subsets. Initially, the method breaks the set of all solutions into two mutually exclusive subsets. Subsequently, these two subsets are partitioned into two smaller subsets, and so on. The process of determining how to partition the subsets is called branching. The bounding aspect, meanwhile, of branch and bound determines upper and or lower bounds on the best solution contained in any subset of solutions. And in a maximization problem, a subset whose upper bound is less than the value of a known feasible solution will be excluded from further consideration and would be placed under the bucket which is considered as not promising anymore. Take note that branch and bound is a general approach rather than a specific procedure for a given problem. That is, the branching and bounding rules will differ for each type of problem. Let's look at this example for application of branch and bound. Consider the following 0-1 integer programming formulation of a 5-item knapsack problem. So if you would recall the very first example we had during our first lecture day, you have a knapsack and then it has a limitation and in terms of capacity, and you have a certain number of items that you would like to place inside your knapsack. It's just that the total weight of those items would exceed the capacity of your knapsack. Therefore, you have to determine which among those items you are going to place inside your knapsack without going over the capacity of the knapsack. And your criterion for determining which item you place inside your knapsack depends on the value that you allocate or assume for each of those items. Okay? And if you decide to place a particular item inside your knapsack, then the variable representing that item gets a value of 1. Whereas if you decide not to place the item inside your knapsack, then the variable representing that item gets a value of 0. So this is a 0-1 integer programming formulation, or a yes or a no scenario. So you have here your objective function equation, which is to maximize the value that you place inside your knapsack, the coefficients of which represent utility values, or the level of importance that you give to each of those items. And then the coefficients in the constraint represent weights, with the right-hand side value representing the total weight capacity of the knapsack. So if you would add the coefficients of your variables in the constraint, definitely that would exceed the right-hand side constant, which is the maximum capacity of your knapsack, which is only 90 pounds. So looking at your mathematical model, the last row there is x sub I is equal to 0 or 1, which is your integer restriction, wherein each variable can only assume a value of either 0 or 1. So each item must be selected in its entirety or not at all, and fractional parts are not allowed. The bounding part of branch and bound algorithms is often accomplished by model relaxation. Relaxation, in a mathematical programming context, refers to loosening or dropping restrictive assumptions initially. Okay? So the way we are going to approach branch and bound is that initially we are going to relax or loosen a particular restriction, and that is the integer restriction, without losing sight of that objective, because our main objective is still to end up, after the entire process, we need to end up with a solution wherein all values of your variables are either 0 or 1, or all of them are integers. The most common relaxation is the linear programming relaxation, in which the integer restriction is dropped and then the variables are treated as if they are continuous or allowed to have decimal positions. Going back to our mathematical model, our integer restriction in this mathematical model is your last row, which is your x sub I equal to 0 or 1, meaning all your variables can only assume values of either 0 or 1. If you're going to relax this particular mathematical model, then you now have the integer restriction changed to x sub I being less than or equal to 1 but greater than or equal to 0, meaning you are initially allowing your variables to assume values from 0 until 1, or 0, 0.1, 0.2 until you reach 1. Okay, so that is the first step. We relax the integer restriction. Now, by computing the ratio of value to weight, the optimal linear programming solution is obtained by simply loading the knapsack with the highest ratio items first until the capacity is depleted. So you now have in the table the 5 items involved, their relative values, their weights, and then we computed the value to weight ratio to determine the optimal way of determining which item you're going to place in your knapsack first. So of course, we begin with the item with the highest value to weight ratio, and that is your item number 1. Item number 1 has a weight of 30 pounds, so that is definitely still within your 90-pound capacity, and therefore item number 1, or x sub 1 representing item number 1, gets a value of 1, meaning we decide to bring item number 1 along. The next item with the highest value to weight ratio is your item number 2. It has a weight of 36 pounds. If you add that to your initial weight of 30 pounds, then you have a total of 66 pounds, which is still within your 90-pound capacity. Therefore, you can also decide to bring item number 2 along, and therefore x sub 2 representing item 2 also gets a value of 1. The next item with the highest value to weight ratio is now your item number 3. Item number 3 has a weight of 32 pounds. It's just that if you add that to our running total of 66 pounds, you are definitely going to exceed your capacity of 90 pounds. So the question right now is, since we are relaxing the integer restriction, what portion of item number 3 can we still place inside your knapsack without going over 90 pounds, knowing that you already have 66 pounds inside your knapsack. So we are now looking at a fraction of the 32 pounds of item number 3. We are looking at the portion of item number 3 that can still be placed inside your knapsack without going over 90 pounds. So since you already have 66 pounds inside your knapsack, then 90, which is the maximum, minus 66 would give us 24 over 32, which is the weight of item number 3. So that is now the portion of item number 3 that you can still place inside your knapsack. So since we have already completed the total weight of the knapsack, then we now substitute these values of our variables to our objective function equation. So since we have completed already the total weight, then that means x of 4 and x of 5 representing items 4 and 5 would not anymore be considered to be placed inside your knapsack, and therefore they would be assumed values of 0. So again, to substitute those values of our variables to your objective function equation, this would result to 60 multiplied by 1 plus 54 multiplied by 1 plus 32 multiplied by the quantity 24 over 32 plus 0 plus 0. So that would leave us with 60 plus 54 plus 32, or z is equal to 138. So this is your initial solution. It's just that we are not satisfied with this solution because one of the variables is not an integer solution, or it is still in fraction form. Again, we are initially relaxing the mathematical model, but ultimately our goal is to end up with a solution wherein all variables would only have integer solutions, or in this case, a choice between 0 or 1. So given that the initial solution is not an all-integer solution, there is a need to implement a branching process to partition the set of all solutions into smaller subsets. Since the knapsack problem involves answers of either 0 or 1 to the variables, then the partitioning process will create a binary tree. So the first node that you see in this slide represents our initial solution, wherein the objective function equation yielded a value of 138. And then you have there the values of the variables, wherein one variable is still a non-integer solution. So when we now branch, we now test for that variable that did not give us an integer solution, which is our x of 3. So what are the possible integer values that x of 3 can assume? So since we are dealing here with a 0, 1 integer model, then x sub 3 can either have a value of 0 or 1. So you branch out, wherein the left branch would assume that x sub 3 would have a value of 0, or you would not consider placing item number 3 inside the knapsack, while the right branch would assume that x sub 3 is already inside the bag, and therefore x sub 3 already has a value of 1. So you now have initial assumptions for your x sub 3 before going back to your data and analyze it again. So let's do that. For the left branch, we are assuming that x sub 3 is equal to 0. Looking at our data, the item with the highest value to weight ratio is item number 1. It has a weight of 30 pounds. So adding that to the fact that item number 3 would not be placed inside your knapsack, therefore it is still within your 90-pound capacity, and therefore x sub 1 representing item number 1 gets a value of 1. And then the next item with the highest value to weight ratio is item number 2. Item number 2 has a weight of 36 pounds. Adding that to your initial weight of 30 pounds would give us 66 pounds, which is still within your 90-pound capacity. Therefore, x sub 2 representing item 2 also gets a value of 1. Now, since item number 3 would not be considered for this particular branch, looking now at our data, the next item with the highest value to weight ratio is now item number 4. Item number 4 has a weight of 24 pounds. If you add that to your running total of 66 pounds, you are going to get exactly 90 pounds. Therefore, the entire item number 4 can still be placed inside your knapsack, and x sub 4 gets a value of 1. And since we have already met the 90-pound capacity of your knapsack, then we again stop at this stage and then compute for your resulting objective function equation value by substituting the values that you have for your variables, wherein in this case, x sub 5 would also be equal to 0. So substituting the values of x sub 1 equal to 1, x sub 2 equal to 1, and x sub 4 equal to 1 to your objective function equation, the resulting value of z would be equal to 132. And that is based on an all-integer solution, wherein all our variables now have values of either 0 or 1. It's just that at this stage, we cannot yet say that this is our final answer or final solution, because there's still another branch hanging. Okay? If upon analysis of that remaining branch, if it would yield a value of z higher than 132, then that would be a better solution than the 132, because our objective here is to maximize the value of z. Okay? So in effect, that 132 is the upper bound of that branch. Okay? But the 132 is currently also the lower bound of our solution. Okay? Against which you are going to compare other branches. But for that branch, the left branch, that is already the upper bound. You don't have to branch further below because you already got an all-integer solution. It's just that if you now compare that branch to other branches, then the value 132 is now your lower bound. Okay? What does that suggest? That suggests that if in analyzing your right branch, if it would yield a value of z lower than 132, then that means that branch is not anymore considered as promising. Because in the branch and bound method, when you further go down your branches, the value of your z would continue to decline. Okay, so if the value of the right branch in this instance is already lower than 132, then there's no use in further analyzing that branch, because as you further go down, the value of your z would just continue to go down, and therefore the 132 would continue to be better than whatever value you're going to get from the right orange branch. Okay, but if the right orange branch would yield a value of z higher than 132, then that means that branch remains to be promising, or it can still yield a solution that is all integer, and yet the value of z is higher than 132, and therefore that would be better. So let's now analyze your right orange branch. In that branch, our initial assumption is that item number 3 is already inside your knapsack. That means you have an initial weight of 32 pounds inside your knapsack. So looking now at our data, the item with the highest value to weight ratio is your item number 1. It has a weight of 30 pounds. Adding that to your initial weight of 32 pounds would give us a total of 62 pounds, which is still within your 90-pound capacity. Therefore, you can still bring your item number 1 along. And therefore, x sub 1 representing item 1 gets a value of 1. And I forgot, when there is no further need to branch from a node, the node is considered to be fathom. So the node containing the value of z equal to 132 is already considered fathom. To proceed. So again, in our analysis of the right-hand branch, item number 1 can still be placed inside your knapsack. Therefore, x sub 1 representing item 1 gets a value of 1. Next item with the highest value to weight ratio is now your item number 2. Item number 2, however, has a weight of 36 pounds. If you add that to our running total of 62 pounds, definitely you are going to exceed your 90-pound capacity. So again, what portion of item number 2 can we still place inside your knapsack without going over 90 pounds, knowing that you already have 62 pounds inside your knapsack? So that would simply be 90 minus 62, or 28, divided by the weight of item number 2, which is 36. So you would have a ratio of 28 over 36. So we still have a non-integer value in the right-hand branch. But at this stage, let us just first compute for the resulting objective function equation so that we can test whether we can continue analyzing this branch or we can already stop the process. Because again, if the value of z in the right-hand orange branch is going to be lower than 132, then we don't have to further analyze the right orange branch. But if the value of z would be higher than 132, then that right orange branch continues to be promising. So if we substitute the values of the variables in the right orange branch to our objective function equation, we are going to get a value of z equal to 134, which is still higher than the value of z we got at the left orange branch. So that means the right orange branch continues to be promising, and therefore we continue the process. So in our analysis of the right orange branch, the variable that did not give us an integer solution is your x sub 2. So that is now what we're going to focus on. So the possible integer values that x sub 2 can have are x sub 2 equal to 0 and x sub 2 equal to 1. So those are the two initial assumptions that we would have for the next level of nodes that we're going to analyze. It's just that when you branch downwards, in order for you not to go in a cyclical manner, you have to also assume downwards the initial assumptions you had coming from the mother node. So the two blue nodes came from the right orange node, wherein the initial assumption is that x sub 3 is equal to 1. Therefore, you have to also use that assumption when you analyze the two blue nodes. Okay, so that means when we now analyze the left blue node, our initial assumptions are item number 3 is already inside your knapsack, and item number 2 would never be considered in our analysis. So that means you have an initial weight still of 32 pounds. So going back to our data, the item with the highest value to weight ratio is item number 1. It has a weight of 30 pounds. Adding that to your initial weight of 32 pounds would give us a total of 62 pounds, which is still within your 90-pound capacity. Therefore, item number 1 can still be brought along, and x sub 1 representing item number 1 gets a value of 1. Since item number 2 would never be considered, based on our assumption in this left blue branch, and item number 3 is already inside your knapsack, then the next item with the highest value to weight ratio is now your item number 4. Item number 4 has a weight of 24 pounds. Adding that to our running total of 62 pounds would give us 86 pounds, which is still within your 90-pound capacity. Therefore, item number 4 can still be brought along, and x sub 4 representing item number 4 also gets a value of 1. But we are not yet done because we still have some space left for our 90-pound capacity. So we proceed with the last item in the list, which is our item number 5, which has a weight of 26 pounds. But we all know that there's only 4 pounds left. Therefore, the only portion that we can bring of item number 5 inside our knapsack is your 4 over 26. So given those values of your variables, if you now substitute those values to your objective function equation, you are now going to get a value of z equal to 112, which is already lower than our lower bound, which is 132, the one that initially gave us an all-integer solution. And since, as I said, as you further branch downwards, the value of your z would continue to decline, then there's really no impetus for us to further analyze the left blue branch, and therefore we stop analyzing that branch. We now have the right blue branch. In the right blue branch, we're now assuming that items number 2 and 3 are already inside your knapsack. Therefore, you have an initial weight of 68 pounds. So going back to our data, the item with the highest value to weight ratio is your item number 1. It has a weight of 30 pounds, but adding that to your initial weight of 68 pounds would exceed your 90-pound capacity. So what portion of item number 1 can you now still place inside your knapsack without going over 90 pounds? So that would be 90 minus 68 would give us 22 over 30. If you now substitute those values of your variables to your objective function equation, you are now going to get a value of z equal to 130, which is also lower than the 132 lower bound that we have established earlier. And therefore, we again disregard further analysis coming from the right blue branch. And since there are no other branches to analyze, only then can we assume that the analysis wherein we got the value of z equal to 132 is our final answer. which means that the only items that we are supposed to put inside our knapsack would be items 1, 2, and 4. This is your branch and bound method for solving integer programming problems.